Kia ora tātou, ko Andrew Sargent, tōku ingoa. And today will be the Level 3 Aqueous Systems exam tutorial. So this will just be a continuation from last night with Deline Home. These tutorials are brought to you from Study It. So in the description, there will be a link to Study It where you can go to after this if you have any questions. I have also put in the description the link to the folder that wasn't there last night, but it is there now. And there's also the link to the document that Deline will be going through today. So other than that, over to you, Deline.
Right, kia ora. Ko Deline Holm toki ingoa. Now, for the Aqueous, so this is the last of the three, and if you like maths, then this is one that has the most maths in it. You will, of course, be given a resource booklet, and please make sure you use it because you are given for this exam a whole lot of equations, and you are also given the complex ions. So in the past, you had to learn the complex ions off by heart. Now they are given. So please make sure you do use it and don't try and rely on your memory. Most of them need 4 OHs or ammonia or cyanides, but there are exceptions. Silver has 2 cyanides in its complex or 2 ammonias in its complex, and nickel has 6 ammonias in its complex with ammonia. So please make sure you refer to that. Then also in terms of the given information, it depends on how your teacher taught you. Some teachers teach only using Ka or pKa. Others use Ka as well as Kb, and I will do some of Kb because I like that method. But notice that the only equation given relating to this is the Ka. You have to then change from, if you want to use the Kb, you need to get it from the Ka. Also notice these 2 equations over here. I will be referring to them later when we go through some past papers. The Ks equals S squared. This is a solubility equation because Ks is the solubility product. And you can use this for A, B salts. So what we mean by that is 1 cation to 1 anion. So calcium carbonate. For this equation, you use this for A to B salts or A B2 salts. So this is when there's either 2 cations for every 1 anion or 1 cation to every 2 anions. So this could be something like, for example, silver chromate for the first one, or perhaps like calcium hydroxide for the second one. So this is when you use these 2 equations. You only use them also when it is in pure water. There is only one source of each cation and anion, and that is from the salt. So I will highlight that just now. So this is in the resource booklet, which will be given to you. So please make sure you use it. Let's now look at this document. And as I say, there should be a link to it. What I've done here is I've taken the last 4 exam papers. I've categorized the questions into 9 different parts and looked at and also added the assessment schedule, so you can see clearly what's an achieved question, what's a merit question, what's an excellence question, and you can look particularly at the wording and what is needed to get your merit and your excellence. So the first thing is that normally starts, so you can see last year it was question 1, the previous year it was question 2, but it tends to be always question 1. They normally give you a substance. So last year it was magnesium hydroxide, the previous time lead bromide, and you are asked both to write the solubility equation and the solubility expression. So this is the equation. Okay, obviously with the equation, notice the arrow. Do not use a normal arrow, because a normal arrow shows it's going to completion. You must use the equilibrium arrow, and this is the expression. No, there's no cheat sheet for this one, because it doesn't have very many explanations. And I'll be going over the explanation. It's now more mathematical calculations for this particular one. Okay, now this is just an achieve, but notice you have to get both correct. Now, I always insist that people put in the states, because you should always put in states at level 3, but notice that they're not too particular for it. Like they haven't given states here. But if you got into that good habit, please, do include the states. So simple, straightforward, and again, you only need about 8 or 9 achieve points to achieve this paper. So there's a first dead easy one. Just make sure that everything is balanced, and you have to get both correct. You'll notice it's always both this and the KS expression. So that's straightforward achieve to get you going with a nice easy question. The next one that's normally always follows is also an achieved, and it can go to merit question depending on if they give you a little bit extra in there. And this is where you use that KS is equal to S squared. So KS is equal to S squared, or KS is equal to 4S cubed. This is only when there is a single source for both the ions. So both the cation and the ion come from one place and nowhere else. So an example of this, a clue, it always says in water. It's not in another solution, or nothing is being added to it. So if it says calculate the solubility of whatever the substance is in water, they have to give the 25 degrees simply because the value is for 25 degrees. So now you know if it's something like this straightforward, all the hydroxide and all the magnesium can only come from the magnesium hydroxide. It means we can use these equations. And of course, this is, hopefully you can see, 1 cation to 2 anions. So it is an AB2 salt. So you would use this. Now, it's always a good idea to have a good impression straight away so that the examiner knows, hey, this person knows what they're doing. A lot of students just simply go, KS is equal to 4S cubed, therefore S is equal to, and they spit out the answer. Please say what S is. So let solubility be S. So you're sort of saying what that S stands for. It stands for solubility. And you're going to make the concentration of magnesium equal to S. And therefore, because there are 2 hydroxides for every 1 magnesium, the concentration of magnesium is 2S. But otherwise, then it's a straightforward put into the equation, solve for it. And remember, please, whenever you have a concentration, you need to have a unit. Notice there are no units for KS values or Ka values, at least not at NCEA level 3. So if you're asked to calculate a Ka value, given sort of concentrations that you've got to use, the Ka or the Ks value does not have a unit. pH also doesn't have a unit, but concentration does. So carrying on, this is fairly straightforward. So you'll notice, can you see it's a sort of standard follow on, and you'll notice always that in water at, sometimes they might say in pure water, but you know that's when you can use the Ks equals to S squared or 4S cubed. Right, so here's an example where they've taken the cube root, so it's gone the, that's a straight 4S cubed. Okay, sorry. Okay, now you will always then get 1 or 2 questions where the ions come from different sources. And in this case, you'll know because, can you see it's they avoid the in water. You'll notice that's not there. And you'll see there's another substance present. So you've got to use MgOH2, but they give you another substance. So the moment they give you like two different substances that are not the same, you can't use that S squared or 4S cubed expression anymore. You have to develop it from the Ks expression. So you would first write the equation, then the expression, and then you'd go, okay, now obviously because I've chopped up this question, you can't see the Ks value, but it would have been given in part 1. So you can substitute for the Ks because it would have been given. You are asked to calculate the concentration of magnesium, so that's the unknown. And then you know the concentration of the hydroxide. Now, notice it looks quite a sort of like a complicated thing. Why didn't I just use 0.120 to substitute into the concentration and square it? There are a few tricks that they can include in the question for this. The one is where they mix two solutions. So if I've got a solution that is, say, 0.1 molar, so I'll just say there are 2 bits to it, and I mix it with another solution, which is, say, something else. So I'm going to make it the same concentration. But when I pour this into that, I am going to have double the volume, but with only 2 bits in it still. So the concentration is going to change because you've changed the volume. So that's what this little thing over here is for. It's to show that my concentration isn't 0.120 anymore. It's my new volume is 50 milliliters now, the 30 plus the 20, but I only had 30 mils of this concentration, so you go 30 divided by 50. No cheat sheets. Right. So that's the one trick where you mix 2 solutions together. Sometimes they won't give you a volume and they'll just simply say equal volumes of such and such were mixed. So if you're mixing equal volumes, you know that your concentration is, a half now. You divide by, so in other words, instead of 0.12, if I mix it with equal volumes of the other one, then it's going to be 0.06, okay, because you've halved it. So that's the first trick. The other trick they could do is they may not even say this. They may just simply say that you put the magnesium hydroxide into a solution that has a pH equal to, let's guess, it could be acidic or it could be basic. So let's say a pH of 9.5. Okay, so now you go, well, what is pH got to do with this? Remember, pH is the concentration of hydrogen ions, which is relative also to the concentration of OH minus ions. So you first need to work out the concentration of OH minus ions based on the pH, and then that gets inserted into this expression. Okay. Any questions on that? Now, I'm just checking, can everybody see the document I'm working with?
Yeah, no, I can see fine.
Yeah, okay. And I suddenly realized I had frozen my video, and that's why there was a problem. Because I was wondering why it wasn't changing. Okay, right. Okay, so these are fairly straightforward as long as you are aware that you've got to change the concentration when you mix 2 solutions. And also, they could also give it to you in terms of giving you a pH instead of a substance. Right. So that is one way they're going to ask you when the ions come from different sources. The other way they're going to ask you this question, so you'll notice this does go to excellence level, and you've got to show the full working. And So the next type of question is, will a precipitate form? So when you do this type of question, and I'll just link it to that first one so you can see the difference. Oh, come on. The first one, if I just tidy it up, we are using the Ks expression because it is at equilibrium. So Ks is the constant when the system is in equilibrium. If, however, I am mixing two solutions and I want to find out will something precipitate, it is not at equilibrium. So I calculate by using what we call the ionic product. So you use something like IP. Your teacher may have given you something different. So if you've learned something different to IP, because there are various ways you can use it, but otherwise just say IP for ionic product instead of for the Ks. But otherwise you do exactly the same calculation as you did before. So can you see we have got, now this is really tricky because they've done the two things together. They've added two solutions and they've given you a pH. So you first work out the OH minus concentration from the pH. Then you work out the new concentrations. Can you see by adding 65 to 40, it's 105. So that's to work out the new concentrations. You now get a value. Now remember what I said, Ks does not have a unit, so there's no unit there. And you have to, for this, so you'll notice there, you have to, for excellence, put in your comparison. So this statement is ultra important for merit and for excellence. So you've got to say Rp is equal to Ks, is greater than Ks, and therefore, because the ionic product is greater than Ks, you will get a precipitate being formed. If it was the other way around, you wouldn't get a precipitate. If you're really desperate and you don't know what to do, correct comparison of Rp with Ks would give you a tip. So you could even just guess and just make a statement, work out any arbitrary value, and you've got a 50% chance of being correct because it's either bigger or smaller. Not recommended, but it's at least better than a blank answer. Right. So that is normally would be sort of two questions that could get up to excellence level. The other excellence question, which is the explanation question. And so I'm just going to go over here because these are all the same sort of things where you'll see the same sort of things come up. You've got to now use equilibrium principles. So what you have to do over here is often they'll say no calculations required. So when they ask you this question, will you get a precipitate, or what happens when you add this to that? Then in the explanation, you've got to think of three things. Is the solution going to be affected by a change in pH? In other words, magnesium hydroxide is a hydroxide. So if you change the pH, you're going to be changing the OH concentration, OH minus concentration. Or it could be more subtle than that. It could be, and say, like, for instance, ammonium salts are actually all soluble. But it could be something where it could be based on a weak acid or a weak base. And therefore, don't just look for the obvious. So always think, will my substance be affected by a change in pH? Because if it is, and the question says they've changed the pH in some way, you need to discuss it. The other thing you've got to think about is the common ion. So in other words, I am adding OH minus by adding sodium hydroxide. I have got magnesium hydroxide, so my common ion is the hydroxide. I am adding hydroxide to hydroxide, so there is my common ion. I need to discuss that. And then the thirdly and lastly is you've got to think of, will I have a complex ion being formed? And this is when you definitely go to the resource booklet and you look, you look to see will I have any complex ion being formed? Now, in this case, remember we had magnesium hydroxide, so we don't have that issue over here because there's no complex ion involving magnesium. But if you were given, say, lead hydroxide or zinc hydroxide or nickel or something like that, then then there's a strong possibility of the complex ion being formed. Okay, so have a look to see what they want from, because this is a fairly simple one. It really only looks at the common ion, because we don't have a complex ion, and we haven't said much about the pH. They haven't said that in the question. So they're just simply saying, I am adding OH minus through sodium hydroxide. And then you've got to say, why does the concentration of this decrease? Now, always, yep. So if there is a complex ion, you always write the equation, and that's what I'm going to be saying right now. Always write equations. That's an absolute. And if you need more than one equation, write them all, and then go ... This is equation 1. And then say you had a complex ion one, you would go ... equation 2. So when you are explaining, you don't have to keep on writing out the explanation, because what is a common thing over here is people say, if you add hydroxide, then the equilibrium position will shift to the left, and therefore there will, and I'm going, what equilibrium? You haven't told me what equation you're talking about. So always say addition. I mean, here they've done it very briefly. I would have preferred a much more detailed one, but it's basically saying you're adding OH minus, so you're increasing the concentration of OH minus. And you'll see that they've specified that OH minus is a common ion. So as a result, I would have said the equilibrium favors the equilibrium in equation 1. They've only got one equation here, so it's not too bad. Favors the reverse reaction. And why? Say why it's doing that. Because it's got to try and get rid of that added OH minus. So it's got to, they've said here, to consume some of the OH minus or to use up some of the OH minus is fine. And because the equilibrium position shifts to the left, or if you say the equilibrium favors the reverse reaction, you're going to get more hydroxide being formed. Now, this extra thing over here is because there was another part of the question. So that's what happens when you chop things up, unfortunately. You go, well, where's the calculation? And that's really because there was another part to the question. Okay, so now here is an equation where everything happens. Okay, can you see you've got the pH being changed? So you've got to think, how is that going to affect it? Because if I'm decreasing the pH, I am increasing H+, or so that's increasing, or I am decreasing the OH minus concentration. I have nickel. Nickel, look in the handbook, that gives a complex ion. And for the first bullet point, I've got to discuss when I'm adding ammonia. So that is my complex ion. It's the nickel ammonia complex ion. So again, you can go through and see exactly what you need. Now, the way they have done it is they've written the equation, given the explanation, written the equation, given the explanation, written the equation, given the explanation. Or you can write all three equations and go ... equation 1, equation 2, equation 3, and then you can just say, the equilibrium position of equation 1 shifts to the left, or that sort of thing. Right. So that is pretty much then everything you need to know about solubility, which usually takes up 1/3 of the paper. Sometimes it takes up more than 1/3, but it's usually 1/3 or less of the paper. 1 year they had this one, thiocyanate. That was because it was based on what you would have done in level 2 ions, but now that has sort of changed. They can give you other complex ions. So they but they would normally say something perhaps about it. Or if you go, well, why on earth is thiocyanate being added? It means that there was a complex ion being formed. You may not know the formula for it, but have a go anyway. You may not get excellence, but you can still get merit. Yeah. So they give you, they can ask you anything from the given list of complex ions. They could also ask from others, but usually they would now give a clue. This change where they've added the complex ion has only happened in the last 2 years. So we're still sort of seeing what they're going to be doing. Yep. So for the complex ion to form, you need lots of it. So if I go back to, say, an ammonia one, if I added ammonia, let me go back to, say, over here. Say this wasn't sodium hydroxide. If I added ammonia is a base, so it's going to increase sodium, it's going to increase the hydroxide ion in solution, which means when I first add the ammonia, I'm going to get more zinc hydroxide precipitating because I have increased my pH. So that's why I say with pH, you've got to be careful. You know, there's little ways they can hide the information. Ammonia is one of them because it is a weak base. So adding a little bit of ammonia, I'm increasing the pH. So that's like a common ion because I'm adding more OH minus. So I'm going to get more of this precipitating. But as I add more ammonia, then I will get the complex ion being formed. Because remember, for the complex ion, I need 4 ammonias for every 1 zinc. So, you know, you need lots of it. Okay. Right. Let's carry on because there's a lot of things you need to know. The next section is really everything about strong and weak acids and bases and their salts, the properties of them, and the relative order of concentration. Often the calculations are linked to the titration, so these questions are a bit chopped and changed a little bit. The first thing you need to know, under the assessment specifications for this year, you are supposed to know SA is strong acid. You are supposed to know these. So if they, in the question, give either HCl, HBr, HNO3, or H2SO4, you're expected to know that those are strong acids. They won't tell you. Similarly, for weak acids, if you're given hydrogen fluoride, ethanoic acid, or the ammonium ion, and it can be in the form of a salt like ammonium chloride or ammonium nitrate or something like that, you're expected to know that those are weak acids. Strong bases, potassium hydroxide, sodium hydroxide. Weak bases, ammonia, methyl ammonia, or methylamine, and the ethanoate ion. So those you are expected to know. They can give you others, but if they do so, they will tell you. A good tip also to know whether something is weak is they'll always give you a Ka or a pKa value. Strong acids and strong bases are not given a Ka or pKa value simply because we say the equation has gone to completion. So basically, if you can't divide by naught, because remember, it's products over reactants. So if it's gone all the way to products, you're dividing by naught. I mean, in reality, it's by such a tiny amount. So we just don't give Ka values for strong acids or strong bases. Now, in terms of properties, you'll notice they'll always give you something like this. And can you see you must write equations? Always for explanations. If you don't have an equation there, you know you're not going to get excellence. Okay? So when it says fully compares, it means, and include at least one relevant equation. So write equations. So if you are given these substances, write the equation for when it dissociates in water. And remember, with the equations, be careful of the full arrow as shown over here for the methylammonium chloride. That is a salt. So a salt dissolves completely. So you use the full arrow because it goes completely to the right. Compared to a weak acid, where you use the equilibrium arrow. And again, you should be putting in your states, but they don't seem to be too fussy over here. So you'll notice you have to state whether they're weak acids or weak bases or so on. You've got to talk about the degree of dissociation. So you'll see they've said something about that. And therefore you've got to talk about the property. So if it dissociates less, then it's going to have fewer hydronium ions in solution. So the pH is going to be higher. So in this case, they've asked you to relate it to the given pKa values. So make sure you respond to that in your answer. If you're given a salt, or if you're asked about the conductivity, then remember what you explain conductivity. You need charged particles to move, and obviously the more charged particles you've got, generally the better the conductivity. It's not almost always, because there are other things like how big is the size of the anion and cation and so on, but we won't go there. You don't need to know that for level 3. Okay, so no questions so far. You're all doing well. And you need to also order them. Now, in this particular case, you just got to include, just add it in, and they've just said greater than and equals. They've already put it in. Other times they might just simply say solutions of equal concentration were prepared. Rank the solutions in order of decreasing pH in the box below. So I've just left out the box. And then you've got to justify it. So if we just take, say, this one, remember that was one of the list. You should recognize it is a strong acid. So a strong acid dissociates completely, which means there's no HBr left. You always tend to leave out water. So basically all what you've got is H3O plus, which is equal to the bromide. Okay. And you've always got the OH minus. In your explanation, you need to, of course, have the equation. So you'll have your HBr going completely to plus H2O, sorry, H3O plus Br minus. Okay. And then when you want to explain this part, then you would say H2O is an equilibrium with with H3O plus OH minus. Sorry, that 2 isn't there. Now, it's useful to also say Kw is 10 to the minus 14, which is given. And that shows, because this is so tiny, hopefully you'll know that most of water exists as H2O and not as hydronium and hydroxide ions, compared to, well, this is a strong acid, so it goes completely to the other side. But when you're comparing it, say, to a weak base, this value is always round about, say, 10 to the minus 5. So you can see that this Kw is orders of magnitude smaller. So you've only going to have a really, really tiny amount of hydronium ions in this basic solution. So if you just look at the answers, okay, they've just given it like that. I would have preferred to have said my weak base is in the greatest concentration. Oh, sorry. Okay, sorry. I thought it was going to be in order of the particles. Sorry, I misread the question. I'm rushing through it, but this is the explanation. And so this is also where you anything to do with properties, pH, and so on. This always gets you to an excellence question. And notice they say includes at least 2 correct equations, of which one of them must be the ammonium one. So always, if you haven't got equations in there, go back and add them. So here's an example again. They've just done it in order here. I would prefer the greater than and the equal sign, because I think that gives a lot better understanding. And it also helps you sort of know which one should come first, because this is more or less in equal amounts, and that one will be the tiniest because I've got a basic salt over here. Notice if I have a basic salt, sodium ethanoate, you would start off with the first equation of CH3COO minus Na plus. Being a soluble salt, it will go completely to the anion and the cation. And then you would do the hydrolysis of the anion to form the acid and the OH minus. Always do a charge balance. So I've got a negative charge on this side and a negative charge on that side. That will help you check whether you made the silly little error by writing H3O plus by mistake when you actually meant hydroxide. Right. So there's, as I say, definitely you're going to get something like that, and that's definitely an excellence question. And always make sure that your equations are balanced and so on. Do a charge balance. Right. Let's carry on. Okay, so you can see this always carries on here. Now you're going to have questions based on fairly straightforward calculations. They're normally achieved on merit level, where you just use the Ka expression to calculate the concentration of something when nothing else is present. So concentration of a base and nothing else has been added, or the concentration of an acid if nothing else has been added. It's the equivalent of the Ks in pure water. So here is an example. It was part of a titration, and they're saying I've got a pH of 2.78. Show that my acid concentration before I've added any base is this amount. Now, if you do physics, you also probably know when it says show, you do the full working. So I always say, do the EEC method. EEC, equation, expression, calculation. Okay, I can't spell, but anyway, the EEC doesn't quite work. So always write the equation first. That means you're going to write the correct expression, because if you have a Ka expression, you must have the H3O plus in the equation. If you don't, it's not a Ka expression. Similarly, if you were doing a Kb expression, if you don't have OH minus in it, you haven't got a Kb expression. So that's a fairly straightforward. It goes normally to achieved or merit level. It depends on the year what happens. And as I say, it's the equivalent. So here it's where you've got given a pH, calculate its concentration, and sometimes they'll give you the concentration and they'll say calculate its pH. It's nice when they do it with a titration graph, because you get given the graph and you can actually see whether your answer is correct, because you can check it on the graph. Okay. So you can see these are all from the titration type questions, but I've just put them here as a straightforward. Now, here is an example of a common error. This is a salt, but remember what I said about you've got to know the given weak acids and weak bases. Ethanoate means this is a weak base. So what you would start off with, if you were trying to do this, a lot of students go CH3COO minus, Na plus, goes to CH3COO minus plus Na plus, and then they go Kb is equal to CH3COO minus multiplied by Na plus divided by CH3COO minus Na. Can you see what is wrong here? I'm doing a Kb, okay, because I've seen it's a base, but does this Kb expression have any OH minus in it? And hopefully you can see it doesn't, because I have put Na plus in there. If you've got any cation in, like a sodium cation or potassium cation or calcium cation, you've made a mistake. Okay, they do not appear in your Ka or Kb equations. So you'll notice what they've done here. They've worked it out via Ka, but you could have done it also via Kb. So you could just simply say if the pH is so much, you've got to calculate the pH. So you simply calculate the pOH based on the concentration of OH minus ions, and that's from the Kb is equal to CH3COOH, OH minus, all over CH3COO minus. Now, this value over here is the amount of ethanoate. So you're going to say, as part of your assumptions, is that you assume that the amount of hydrolysis is so little that our denominator is that value. Then the second assumption you're going to make, and I strongly recommend that you write those assumptions down, even though they don't give it in the assessment schedule, is you've got to assume that this amount or concentration is the same as that one, which leads you on to expression where you've only got one unknown, which is the OH minus, because I know this is 0.224, and if the Kb you can work out from the Ka. They will give you the Ka or pKa, and you can work out the Kb from it. So I don't know if you've got any questions on that, but that's a fairly sort of straightforward one. It's just when you're given a salt, students sometimes can go wrong. Okay, let's carry on. So here is the straightforward one. Okay, it's dissolved in water. So now we get to the next one, which is the titrations. And as I say, the first question they normally give is when they've given you the graph, is they'll say, show that the acid has a pH of such and such, or show that the concentration is whatever. So that's what I had before. Then the other thing that you'll find has come up every year in the last 4 or 5 years is you need to calculate the pH of the equivalence point. And the equivalence point is always on the steep part of the graph, and it's always round about halfway. So if you extended this line on with a ruler, and you extended that line on with a ruler, and you measured sort of the distance over here and divided by 2, now you know from the graph what it should be. You know it should be around about 8 point something. So if you don't get an answer of round about 8 point something, you've stuffed up some way. Go and look at where you've stuffed up. So use that graph because it can be really useful. Now the trick with this one is, of course, you've now added 2 solutions. So you have changed your volume, and because you've changed your volume, just like with the solubility one, you have changed your concentration. So that's the first thing you need to be aware of. And then the second part is, of course, you've got to think of what's happened. At equivalence point, all my acid has reacted with all my base, and so all I've really got left, I mean, I've got tiny bits of everything, but all I've really got left is my the anion of the acid and the cation of the base, pretty much. I've just got my salt. Now, the anion of the acid, they normally give you, they can never give you a titration of a weak acid, weak base. That doesn't happen because that'll never go to completion. They can only give you a titration of strong acid, strong base, which is quite rare because you can't ask buffer questions and so on and so forth. They may give you 2 graphs and they could ask you to compare which one is the strong acid, strong base, and which one is the, say, strong acid, weak base titration. And you should recognize that by looking at the start. For a strong acid, strong base, it's normally a sort of a sloping line with hardly anything. With a weak acid, strong base, there's always that sort of bump, and then it sort of flattens out. So just be aware of that. And similarly when you start from the top, a strong acid, strong base sort of goes sort of straight down with no bumps. A weak acid, strong base will go whoop before it evens out. So that's how you can recognize it. Okay. So going back over here, you just need to notice how they've changed the concentration because of that change in volume. And they had to do the solubility the hydrolysis equation of your weak acid anion that's formed, the salt that's formed. The anion comes from the weak acid, so you need to write that hydrolysis. You are given OH minus in this equation, so you can either work with a Kb or you do this change that they've given here to work out the Ka. Okay, but do not use a Ka directly based on this equation because it doesn't work. Okay, so those you'll see it comes up as the equivalence point, comes up a lot. Sometimes they ask you little in-depth questions, and you'll notice then it does come, it gets included for explanation. So now and again, they might ask just a little random question. So we've got the original sodium hydroxide that we're adding all the time is 13.2. So in the graph, why does it actually never ever reach 13.2? And the reason being is, of course, you've diluted it with the original amount of acid. So if I've got in my burette my base, and say I add 50 mils of that, I've started off with 25 mils of acid. So I'll never reach, if I mix those two together, I'll never reach a concentration of 0.163 because, 50 plus 25 is 75. So it's, even though I've got an excess of base, a lot of excess of base, I've diluted that solution, and therefore it'll never reach that. And so you can say here it's the extra 4 mils. I've just made up my own values there, but you can look at the answer and see what it is. Okay, so here's another one, and you can see straight away this is a weak base, strong acid calculation, because you can see that sort of drop before it evens out, the equivalence point is over here. So your equivalence point is round about 3. Okay. You should recognize HCl as a strong acid, and you should recognize that the ethanoate is the weak weak base. So this is a weak base, strong acid. And can you notice, calculate the pH of the equivalence point? So this comes up again and again. So you can focus on the equivalence questions and practice them to make sure that you've got that. And again, if it says no calculations are necessary, make sure that you have probably some equation in there to refer to. It really depends here on the question, but it's always useful to refer to equation. So these are all the titration type, and there's normally one at the start and one at the buffer and one at the end. I've put the buffer ones under the buffer category. That's why they're not here, but you'll notice every year there's calculate the pH of the equivalence point. Right, so we'll just move on from there. The only trick with this is working out whether you're going to use the Ka method or the Kb method, and if your expression matches your equation. Right, so not very many questions coming up. Let's carry on. Okay, so that's still there. Okay, indicator choice. This is, okay, how do you tell if it's a strong base, weak acid, or strong acid, weak base? Right, again, you'll always notice on the graph, because the graph shows you both the beginning and the end. So if you, and the equivalence point will tell you, because a strong acid plus a strong base, assuming that they are both the same concentration, will need equal volumes. But even if they weren't the same concentration, the pH will always be 7 at the equivalence point. Okay? And you can recognize this from the graph, where it either goes a sort of a straight down, sudden drop, and this is sort of a straight slope, or the other way, straight slope, sudden up, and then, so that was went a bit crooked. It doesn't go backwards, but you get the idea. A weak acid plus strong base, obviously there's more base than acid in terms of strength, so your equivalence point is going to be higher. And that's sort of 8 to 10, somewhere in that range. Okay. And you would recognize this if you were starting with the weak acid in the burette, in the conical flask, it would start like that and then tail off. If it was the other way, which I think is what you're referring to, it would go straight down because you're starting off with a strong base, but you'd see it by the equivalence point. So the equivalence point will be at a higher, it will be above 7. So hopefully that's answered your question. Okay, very, very briefly, buffers, indicators, then I'll get on to buffers. So with indicators, remember that the equivalence point, pH, needs to match the color change of the buffer. Of the indicator. So the way we know which one to choose is you need to work out from the pKa, because that gives you like half. So this has what you would use in a titration, where the equivalence point is within 1 pH unit of 1.7. We say within 1 pH unit simply because that's what our eye registers. It registers the color change that roundabout when the one color is 10 times or more the color of the other one. If the ratio of the two colors are not 10 times or more, our eyes can't really pick it up. So here, if it was a weak acid strong base, we would use Nile blue. Okay. And you would explain why. So you can see how they've answered. So you'll notice recently they have asked that question, but previously they have not asked that question. So who knows? Will you get that question this time? I don't know. Right. Buffers. For buffers, there are two types of questions. The one is an explanation and the other one is a calculation. So if you know the Henderson-Hasselbalch equation, I like it and I know it and I use it. It is not one of the given ones. Okay. So you've got to either derive it or you just need to know it. But you can do those calculations just based on the Ka. So based on this, you can do it. So let's look at, so some years there can be a lot on buffers. So if you look at this, what sort of questions can they ask to explain? The first is, what is the buffer region on the titration curve? And it's always where the pH is the same as the pKa for the buffer. For the acid. So if I'm using a weak acid and it has, say, a pKa of 3.75, like over here, then when you see the graph, the titration graph, where it is 3.75 pH, that is the midpoint of the buffer region. And you want ideally to have equal amounts of the weak acid with its conjugate base. I like using that word conjugate base because it's not just any old base that you add. You've got to have that ratio, 1-to-1 ratio of the weak acid with its conjugate base. So if you add more acid, the conjugate base reacts with the added acid, or if you add more base, then the weak acid would react with it. And so spell out the detail. Can you see, as a result, the pH of the solution does not significantly change since the OH minus ions are removed from the solution. So you might think, well, that's so obvious. Well, say it. Okay, so for this case, say it. Talk about also the ratio. You want to try and keep that 1-to-1 ratio as much as possible. Not all buffers have a 1-to-1 ratio. If the buffer isn't 1-to-1, it means it's better at buffering either acid or base. If it's a 1-to-1 ratio, it is equally good in buffering against acid as well as base. Okay. I've seen your question there about what you can derive. You'll see that when we get to the calculations. So let's look at here. What was the question? A buffer is made of a pH of this is made by dissolving this amount in that volume. Calculate the concentration of the acid we have to add. Okay. If you add water to a buffer, it can still buffer the same amount. You've got equal amounts of acid to conjugate base, so it will still act as a buffer. It won't necessarily react as fast because the more diluted it is from your rates of reaction chemistry of level 2 and level 1, the more dilute, the slower it's going to react. And you won't perhaps see any color changes as clearly because it's a pretty dilute solution. Right. Okay, so we've got, so here is an example of a buffer solution. Now, if you're given a mass, if you don't know what else to do, calculate the moles. And that's normally an achieved point. So if in doubt, calculate moles. So if you'll notice over here, you've started off and it says for achieved point, calculate the correct moles of your sodium formate solid. Okay. So that is that very first step. They've calculated moles. Even if you can't carry on and you've no idea what the buffer equation is or what to do, that'll give you an achieved point. Okay. Or in this case, they're not using the Henderson-Hasselbalch. So they have, from the equation, they have written the expression and they have then simply substituted. This part over here was how they calculated the concentration for one of them. That's the number of moles, so you can now work out the concentration because you dissolved it that much in 250 moles of water. Okay, and then now you just simply substitute and you can work out therefore the concentration of the acid. And notice the significant figures, they're getting a little bit more flexible with it. And it's now been saying between 2 and 4. So don't put all the values in, please, that are given on your calculator. And don't just also say 0.6. Okay, they will accept 0.62. So did I answer that in terms of the buffer? Here is another one. Again, the range over which it'll function. Ideally, you want within a pH unit. It's just like your indicator, a pH unit. So this buffer works best over sort of from 8.24 to 10.24. You just add a unit and subtract a unit to get the starting point and the end point. And then whenever you're explaining how a buffer works, please always give equations. Explanations, always think, have I added an equation? Can I add an equation? Okay. They might, as I say, ask you little things like, explain whether the buffer in part 1 is more effective at neutralizing strong acid or strong base. And that is, if you are given the pKa, which you are, of 9.24, if you're told that your the buffer solution is 8.75, can you see it is more acidic than the pKa? So it's not, you don't have equal ratios of weak acid to the conjugate base. So basically, they said, since the pH of the buffer is less than the pKa value, the buffer will be more effective at neutralizing the base. Because obviously we've got a more acidic solution, so we've got more of the acid present than base, and therefore it'll mop up more base. Okay, we've reached 7 o'clock. I hope, Tracy, that I've answered your questions about buffers. What I suggest you do before Friday is sort of download this and have a careful look. They don't give everything needed. You know, as I say, you've noticed they don't give the states and equations. They don't write down the assumptions. They sort of just give the bare minimum that you need. But if you can show off to the examiner that you know about assumptions and so on, put those in. Any last minute questions? Nope. Okay, so just check to see how these questions are answered. You can see the same sort of things come up. So you can just sort of learn the pattern and the little tricks, and you should be fine.
Cool. I think, oh, no, there's one last question. You said over there, Delene?
Oh, what was the equation you said wasn't on the formula sheet? Oh, that is that some teachers use the Henderson-Hasselbalch equation. That is the, where you've got pH is equal to the pKa plus log of the base divided. I always get muddled, actually. It's A over B. So that one, yes, the Henderson-Hasselbalch. So here, you know, you just plug in your pKa value, and then you normally are given those concentrations, so you can just work out the pH. It really depends what they want from the buffer calculation, whether this one is worthwhile or not to use. But as you can see, they haven't used it over here.
Cool. I think that's about it. There doesn't look like to be any other questions in the chat. Right, it's 7:02, so we'll call this a day. Just like to once again thank you, Delene, for spending the time to run these tutorials. Hopefully it has been very helpful for everyone who has been watching. Also like to thank Study It for helping with these, or helping run these tutorials as well. You can go to Study It after this and ask questions if you have them. Just a reminder, the folder is in the description of this video, and this video, the link will be live straight after this, so you can go back to and watch it if you want. Ka kite.